Alright, what's up guys? So we've got problem number 2 today, day 2. So I'll post the problem here again so you can read it. Basically we're comparing a VFD to a ball valve. We're going to figure out the payback to do the VFD over the ball valve. So again, we've got our givens for the original system, VFD, and then the ball valve, all just straight from the problem. And then I wrote down some equations again from the NICE handbook. So I've got a pump affinity law here that we're going to use for the VFD, and then we've got the brake horsepower equation that we're going to use for the ball valve. And then I've got some unit conversions over here on the side that we'll have to use. And so we're just going to jump right into it. We're going to start with the VFD. So this brake horsepower 2 will be the horsepower for the VFD. So we're just going to fill in our numbers. So brake horsepower 2 equals brake horsepower of the original system, 5.3, and then flow at the reduced value, so half of the 500 or the 250. And then we've got the original flow of 500 and then cubed. And so when we plug that in, we will get 0.6625 horsepower. And then when we utilize this conversion here, multiply this by this 0.745, we will end up with 0.494 kilowatts. So the important thing to remember at this point is our VFD is only 95% efficient. So if we were 100% efficient, this would be our pump power, or our brake horsepower. But since it's 95% efficient, we're going to need a little bit more. So we're going to have to divide this by the 0.95 to make up for that loss, the 5% loss at the VFD. And so that ends up giving us, I'll write this over here, that ends up giving us 0.52 kilowatts. Okay, and so now from the problem we know that the pump is going to be run year round. So what we're going to do is, and I didn't write it here, but the cost of electricity in the problem is 12 cents per kilowatt hour. So we're going to do our cost for the VFD is equal to the 0.52 kilowatts times 0.12 dollars per kilowatt hour, and then 24 hours a day for 365 days a year. That will give us a cost of $546.62 for a whole year to operate this system with the VFD. So now we're going to jump down to the ball valve. Again, we're just going to throw our numbers in our equation here. So brake horsepower, ball valve. We're going to do our flow of 250, so 250 gallons per minute, times our head, which is 50 feet. So when we choke down the system with the ball valve, we increase the head to 55. And then we have, this is a unit conversion that's going to get rid of this gallons and put us in the right units. So 3960. And then our efficiency now, so we're a little bit less efficient than the original system was. So because we're choking down the system, we're making everything work harder. And then when we punch that in the calculator, we get 5.182 horsepower. And when we convert units again, multiply that by the 0.757, we get 3.864 kilowatts. All right, and then we're going to do the same thing here for the ball valve. I'll move this line down just a touch. So we do the cost. The ball valve is this 3.864 kilowatts times our price of electricity, so 12 cents again. And then we're going to do 24 hours a day for 365 days a year. And when we do that, we get, it's kind of small on the bottom here, sorry, it is $4,061.84. So as you can see, the VFD is a lot less money in just electricity costs, even though your install cost for the VFD is a lot more. I didn't write it there at the bottom, but the ball valve only costs $3,500 to install. So let's do cost. Sorry, did a bad job writing my stuff on the left here. So VFD is a lot less in electricity costs. It costs more to install, and ball valve's a lot more in electricity costs, but it costs a lot less to install. So now we can just do a payback here. We can say that the VFD, for the payback, our VFD costs $6,500, and then our ball valve costs $3,500, and then we're just going to put that over the electricity cost of the ball valve, so $4,061.84, and then we're gonna subtract this $546. And what this is gonna do is it's gonna tell us the number of years it's gonna take for the VFD to make up for this additional cost that it costs to install in the electricity savings. So once we punch that in the calculator, we get 0.85 years. So in less than a year, the extra cost for the VFD would pay for itself. So, all right, it's problem number 2. Let me know what y'all think.